Hi, Jitesh, we can begin now.
Okay. I'll
Yes,
start
yes,
recording 1 minute.
yes, and then we'll start explaining about the bill.
Okay. So I've started recording. So we can start.
So like team 27, we have some announcement like at 8 minutes and at 8 minute or at 9 minutes 30 seconds, we'll be ringing a bell for like 10 minutes warning. So the bell is it okay?
Okay.
Team 27, did you hear it, right? Like you heard it, right? Provide us a confirmation.
Can you wait for 2 seconds? Actually, there is some audio issue.
Okay, we'll
Just
do
two
this.
seconds. Yeah.
Hello, hello. I'm audible?
Yes, you are.
Yeah. Sorry for the issue.
Yeah, I request you to turn your video on, and then we'll have the demo for the bill.
Can you repeat?
Requesting you to turn your video on, and
Okay,
then
okay,
we
cool.
will have the demo for the bill, and you can begin then.
Okay, cool. Yep.
Hello.
Okay.
So,
Yeah.
team 27 will be ringing bells at 8 minutes and 9 minutes 30 seconds. And the bell is, so is it okay? Is it audible?
Like I could not hear the well.
Just a minute. Is it okay?
No, like is it me or like others? Like even others could not hear.
It's not audible.
Confirm now, please. Was it audible?
No.
Yes.
Oh,
Okay.
were you
It
able
was
to
like very
hear?
light, but yeah, like
Okay, so I think we can work on increasing the volume. Just wait, please wait for 1 minute.
Cool, cool. एक मिनट बस है तो लोग सुन रहे थे Yeah, it was audible.
Great, so you can begin presentation. 27, you can begin.
Okay, so
And
should I
please
start my
turn your video.
screen share? Okay, cool, cool.
Yes, yes. And we'll start the time for the presentation. You can begin.
Okay. So is the screen visible?
yes.
Yeah, cool. Okay. So hello everyone. We are team number 27 and we are here to present our solution for the Cloud Physician PS. I'm Atin and my teammate Sanj, and she'll explain about and she'll continue now.
Uh, so today we would like to present a solution for extracting the vital values from ICU monitor images. The problem of extracting the values of vitals like HR, RR, SpO2, etc. from these is a challenging task, but with the right approach, it can provide valuable information for medical professionals. Our solution basically consists of three stages. So the pipeline for our presentation is the first task is segmentation, the second is classification, and the third is OCR. So in segmentation, what we do, we use a YOLO V7 model for screen segmentation, where we isolate the region of interest containing the vital values from the rest of the image. The second step is vital classification, where we use another fine-tuned UV7 model to classify the vitals present in the the region of interest. This allows us to identify which vital is present in the ROI and where its value is located in the image. And the third one is the OCR, where we basically extract the numbers from the image.
Cool. So let's get a detailed view of the segmentation part. So basically, in the problem statement, right, we get the images of the ICU monitor from a distance. So in the image, it won't be just the monitor; it would be monitor and some extra information. So the first step for us would be to extract out the monitor screen. So and also like we had the segmentation data set, right? So using that, and we decided to use a YOLO V7 model because it's accurate enough, like it's a reasonable accuracy, and it also has a reasonable speed. So instead of going like too accurate or too slow and all, we chose to go with YOLO V7, and we used a pre-trained model, uh, and fine-tuned it on the segmentation dataset which was provided. We had a zero point 0.9 and zero point 0.1 train valve split, and we tried out a few things, and we decided to train it for 50 epochs. And the thresholds we set was like for the confidence threshold was 0.25 and IOU threshold was 0.45. And we tried different methods like based on color, extracting like the screen based on color or some other methods, but those did not work quite well because they could not adapt to the variability. So we went ahead with the YOLO V7. The approximate runtime for this part of this pipeline is around 1.7 second, which is quite reasonable. And then after, this model takes the whole image and crops out the monitor image and sends it to the next part of the pipeline, which is classification. The what we mean by classification is basically detect where the different vitals are, where's the heart rate, where's the respiratory rate, where's the SpO2 and stuff. And we use the same YOLO V7 model. We again use a pre-trained model to fine tune it, and this time we use the classification data set with the same train valve split. So like it, the data set had what do you say, heart rate, RR, all those classes, right? So with those, we could extract out in the new images. If in the inference, we could use this model to extract out the regions of interest. We'll at the end we'll get a list of images with the labels, like which image is which label and stuff. And here the parameters are the same. We kept it as like 0.25 and 0.45, and we also trained it for 50 epochs. And the results we got was the runtime was approx around 1.7 seconds, and the mean accuracy like MAP are the given here. And this basically this model returns a list of images, and then we give it to the OCR, right? We label each image, like which image is corresponds to which class, like first image corresponds to heart rate and all, and then we pass it to the OCR. And the OCR, this is the while training, this is one of the results, like ground truth you can see in the left image, heart rate wave and heart rate SpO2 RR. And when we predicted it, it came out like this. Yeah, as you can see, like some of the labels which are not labeled in the ground truth uh, got also predicted in using a model. And now the OCR part will be continued by Sanj.
Uh, so, like after we perform this, all like these two steps, the final step is the OCR, where we use easy OCR to extract the text values of the vitals from the cropped images. Like this step requires high quality images and a robust OCR engine to ensure like the accuracy of the extracted value. We tried various OCRs actually, and we chose the best one that gave us enough accuracy, but also the time was less. So we tried various OCRs like PyTesseract, TROCR, and Easy OCR. So we found out that TROCR provided the most accurate results, but it was very slow. Like it was very slow interface time. So that is why we went with Easy OCR, which is composed of Craft as text detector, and it uses ResNet plus LSTM based OCR engine. So that gave us the best results. It was fast and accurate as it performed pre-processing, post-processing of input and output very efficiently. We want to say that our solution has various advantages because firstly, YOLO is a very fast and efficient object detection algorithm compared to other candidates that can process images in real time. So therefore, if you want to deploy a solution in real world scenario, the interface time of YOLO would be the most optimal for this problem. Secondly, fine-tuning YOLO on specific data sets can improve its accuracy and like make it well suited for this task. Finally, using OCR on cropped images can further increase the accuracy of the extracted values. And finally, easy OCR is robust and fits well in our case. And this final step took us around zero point 0.5 seconds. So you can say through like the complete pipeline was could be done in less than 4 seconds, which is a very like less time. So like we believe that a solution has the potential to provide valuable information for medical professionals, which can help improve patient care and outcomes. So thank you for your time, and we would be happy to answer any questions you have.
Thank you. So in like when you were using ECOCR, you didn't like run into any problems with respect to BP. Let's say like there was a 123/93, like there was no problems.
Like what we did was using regex, we just extracted only the integers.
Okay. So like what if like that forward slash is interpreted as a one?
Yeah, so the like we put a confidence for that, like so that's and we tried it out and checked what all the possibilities. So there was a like one like occasion where it happened. So we saw its like what was the confidence of its prediction, and then we set a like confidence threshold of around 0.25, so that like it would not predict it as one or something.
Okay.
Uh, okay, so I have one question. So you said like you have made changes that slash is not interpreted as a one, right? But
Yeah.
some cases, like say a monitor is not in a straight line, right? It might be like tilted, a little bit tilted. So in that case, I think like slash will be look like almost similar to like one. So
Okay.
it won't be like a case like it's not interpreted as a one. It's going to be like a case that will be interpreted as a one. So here in this image, right, in the result, you see like there are like iPhone, three iPhones there and slash is there. So it might be like possible if like both of the systolic and diastolic digits are in 3 digits. So final number will come up as a like 7 digit number.
Yeah, like, but the thing is, the slash, right? Like, it's not a one single class or something. The systolic will be the one, and the diabolic will be one. So the slash most of the time got cut out basically. Like, it didn't come at a as
Okay.
a single picture.
So can you please go back to like those digit detection slide?
So we have it slide.
One more back.
Okay.
Yeah. So here like your digit is detecting, right?
Yeah.
So you said like this RR wave and SpO2 wave, right? It's not in label, but it's able to like predict it.
Yeah.
So can you like tell a reason why this is happening?
Like because of the other training points and all,
Yes,
right? It
yes,
learned
yes.
it automatically.
Yes. So isn't there any case when because of the slash is not say suppose SBP and DBP are classified like very short in very like short distance. So it might be not the case when model will predict as a, like one single unit.
Okay, okay, yeah, yeah. Like those kind, like we would have to deal with those kind of corner cases and all.
Okay. Okay.
And then like on the segmentation, can you go to the segmentation slide? So this was you have used like YOLO for that,
Yeah.
right? So after that, like, was there any like transformations like done?
Like after segmenting it out, you mean?
Yes.
Yeah, no, like
So
yeah.
like it would be on like tilted and all, right?
Mhm. We did not do it because anyways the classes like the second YOLO model would crop it out and then send it to OCR. Like we did not like see any particular kind of a use.
Okay.
Okay. Thank you, guys. Thank you.
Thank you.
So
We can close this. Thank you.
okay, thank you.
Can we just wait for 1 minute? My teammates are joining.
Sure. So this is 29, team 29.
Hello.
Yeah.
So team
Hello.
29, there's an announcement for the team. So we'll be giving a buzzer sound once you're 8 minutes and 9 minutes 30 seconds into your presentation for the 10-minute guideline.
Sure.
Is the buzzer audible?
Not yet.
Yeah, please give me a minute.
Yeah, it is audible.
Okay. Good.
All right, can we start now?
Please start. Yeah.
Yes, yes, please start.
All right. Good afternoon, everyone. We are team number 29 here with our presentation for the Cloudphysician track in the Inter-IIT Tech Meet 11.0. We move on to help you understand what the problem at hand was and how we aim to solve the same. The task given was to extract heart rates, SpO2, etc. from the monitor images. We were provided with three datasets for the same: the localization dataset, classification dataset, and the unlabeled dataset. The approach that we used was is to classify in three steps. First, we performed localization, scaling and reorienting the images. Step two, classification, applying OCR and then mapping the vitals. Step three, graph extraction, digitization, and producing the final output. We use several models in a pipeline to target the different tasks at hand, namely YOLO V7, MobileNet, Easy OCR, YOLO V5. YOLO V7 was used for object detection, or better say, localization. MobileNet was used for classification. For targeting the OCR part, we used Easy OCR module. And finally, YOLO V5 for graph detection. We now present to you the entire pipeline. This is the entire roadmap showing all the steps to our final solution. We first took the image, passed it through YOLO V7 and got the bounding boxes, cropped and performed perspective correction on the images as well, and then applied Easy OCR, followed by reading the final vitals. We also perform graph digitization with the help of our YOLO V5 model, as mentioned before. And then we finally classified it using the mobile net model.
All right. So for the first stage of the process, we needed to detect the screen position and crop out the display. Since some images had skewed monitors, we also needed to correct their perspective. For the correction of perspective, we needed the four corners of the screen. So we first implemented the correlated bounding box approach, in which we included poly-YOLO and central poly models. But we soon abandoned this approach because it had like insufficient accuracy. The other approach, segmentation, was rejected due to comparatively high latency, and we ended up training YOLO V7 for real-time screen detection, followed by a novel image processing-based perspective correction, the details of which are in the later slides. For training, we used 1,800 images and 200 images for cross-validation. And there were certain hyperparameters set, and the IOU threshold was set to 0.2, and we tuned the shape and the number of anchor boxes specific to our case. The hyperparameter tuning was a major challenge as it took a lot of time, though at the end, we came up with the best hyperparameters which fit our problem through some clever guessing and some trial and error. Right? Next slide. Next, we did some classification. After some initial analysis, we found that the provided four classes of the 1000 sample dataset were not a true representation of the distinction we set. That is, to differentiate the screens on the basis of the vitals positions, right? Hence, we had to use some semi-supervised methods to have a better classification of the dataset. We used this method on the unlabeled dataset since it provided more variance and had more images. We ran an analysis through which we were able to find out a minimum of 10 different classes were required for proper distinction between different types of screens. For the semi-supervised approach, we implemented the noisy student method, which is inspired by knowledge distillation, in which two models, the teacher and the student model, were trained, for which we used efficient net variance on the dataset. The teacher model was first trained on the labeled images and was used to infer the pseudo labels for the unlabeled images. Then these two were combined, and the student model was trained on the combined dataset with model noise such as dropout and stochastic depth incorporated, right? Which basically encouraged it to learn from the diversity of the predictions made by the teacher model. Once the student model was trained, it became the neo teacher, and this process was repeated for a few more iterations. Finally, on the labeled dataset, so we had labeled it. Finally, we trained a lighter model, MobileNet V3 small, and we got a good classifier with low latency. Okay, next.
Okay, for perspective correction, so what we basically needed was actually the four corners of the screen. And so first, for finding the potential corners of the screen display, in our approach, we first used canny edge detection to get all the edges. Then the edges were passed through a line segment detector from PyLSD library to get all the lines. We then thickened the lines, filled some small gaps, and then filtered them out by some preset length according to our requirement. We then separated the horizontal and vertical lines, and then drew them separately on blank canvases. And all the points of intersection of those two sets were basically our corners, and we did some filtering of removing the corners which were in close proximity. Okay, so the next step was we used heuristics to choose four most likely corners from the selected candidates of corners, which were satisfying some preset condition of minimum area and maximum internal angle difference. Oh, and then after we got the four best candidate for the four screen corners, we then compared with an alternative solution, which is basically just finding the contour directly from the edged image and then approximating using the Douglas-Pucker algorithm, setting the 10% limit on length and then sorting by area. And this approach sometimes occasionally gave better results than our previously one. After we finally got the four corner points, we then passed them to the 4-point perspective transform function to get the correctly oriented screen image. Next slide, please. Yeah. So for the OCR part, first the image was read in grayscale format, and then Gaussian blurring was applied, which was finally followed by adaptive thresholding. The vitals from the processed image were then obtained using the help of ECOCR library. So ECOCR library basically comprises of three main components: feature extraction, then sequence modeling, and then decoding. So the ease of its use and its good performance on the noisy images that we tested on made it the most viable option for reading the vitals. We followed a pattern-based vital mapping technique, which involves first filtering out the unnecessary strings from the red text. Then regex matching was used to find the values for systolic, diastolic, and mean arterial pressure. The respiratory rate was found out by choosing the most suited value in according to its range, which is limited in around 5 to 30. The rest of the integer-only readings were sorted according to their font size with the help of the bounding box area. And also through EDA, we had found out that heart rate was in 95% of cases was written in green. So we selected it by finding the bounding box having the most number of green pixels of certain range in it, and then followed by a sanity check for the value range. So the only thing remaining was the SpO2, and we did some range checks and selected the most appropriate one from the remaining values. Next slide, please. So the graph digitization part, for detecting the heart rate graph, we trained a YOLO V5 model on the training data set provided along the classification data. In the implemented approach, the detected graph was detected graph in the perspective corrected screen was cropped, and then Gaussian blurring, dilution, erosion, followed by thresholding was done to get a binarized plot of the graph plot you can see on the screen. In the binarized image of the plot, the weighted centers of the white pixels of a particular column was used to get the Y value for a given X for corresponding X along the row. Then time series data was the time series data so obtained was smoothened out using we used a moving average with a Gaussian kernel, and finally plotted the digital plot. So next.
All right. For the features, in the end, I would like to list out the numerous novel approaches and the features which made our pipeline more robust, real-time, and gave our model an edge. So we used rectangular bounding box followed by image processing based perspective correction, which allowed for low latency. We used a pattern-based vital matching approach rather than a position-based one, making it more robust and accurate. And then we used a noisy student semi-supervised approach to accommodate for more types of monitor classes, right? And finally, we used easy OCR for the handling of the OCR part, which allowed training custom backbone models, enabling further customization in the future. Okay. Next. Those are our tech stack and citations. Thank you.
Cool. Thanks. So can you bring the deck back, presentation back, and can you switch to the perspective transform slide?
Just a second.
So this step, like how much like time did it take?
So basically, it was completely image processing based. So we were targeting around within at max at least 30 FPS, and in most of the cases, it was satisfying that threshold.
Okay. Any reason why mobile net is it only for because it is like fast enough?
So in for semi-supervised learning in the whole pipeline of teacher-student combinations, we use the different variants of efficient net starting from B0 to B7. And what we found that for the given task, it was kind of an overkill. So we decided once we got the whole completely prepared data set, we would use a light model of MobileNet V3 small for getting the classification task done.
Okay. Cool.
Okay, I have like one question. You have used Kenny edge detector. So in this example, it's giving like correct edges, but I think like sometimes what happens is like monitor edges are not that kind of like visible. So what happens is like Kenny edge detector will detect the edge after the graph in even this example, you can see there is a sharp white line over there. So it will give like bounding box to the just graph and miss out the digits.
Yeah, sure. So like basically you can see also here that there are many edges both inside the screen. So after we got the edge image from the canny edge, and then passing through the PyLSD, which basically gave us all the lines and endpoint coordinates of those lines. So what we did was we then filtered the lines by a set length, which is basically around 0.85 of the aspect ratio of the screen image. So we basically filtered out all the smaller lines, which you can see in the graph, and the vital boxes. They were all filtered out, and we got the length line of our required length.
Yeah, okay. So it's a dependency on like the previous model, like for YOLO, right? You are using that one. So it
Yeah.
depends on the YOLO crop, right?
Yeah.
Okay, good.
And the YOLO was also quite accurate. We were even surprised that just by using only the 2000 dataset, we got extremely well accuracy on the unlabeled dataset also.
Okay. Which model you have used for YOLO?
YOLO V7 one.
Yeah, but which version?
Version 7, I think the official implementation one.
Yeah, but what was the size?
I
There are
think it
like
was the nano one.
Mm,
Okay, so okay, got it. Thanks.
Okay, so we can close this. Thank you, guys.
okay, thanks. Sir.
Thank you.
Okay, thank you.
Can we leave now?
Yes, yes, yes.
Okay, sure. Thank you.
Good afternoon, Team 43.
Good afternoon, Jitesh. Good afternoon, Pradeep.
Good
Good afternoon.
There's an announcement for the team, so we'll be ringing a bell at 8 minutes and 9 minutes 30 seconds into the presentation as a warning. Here is the bell. I hope it was audible.
I don't think I was able to catch the audio.
I'll do it. I'll do it again. Was it on?
Yes, I heard it.
You can start.
So can we start? When will the timer start?
Please start.
Okay, I'll begin now. Good afternoon, everyone. We are Team 43 presenting a submission for the Cloudphysician Vital Extraction Challenge. So we begin by providing a general overview of our code. Provided an ICU monitor image, we first obtain a warped image of the monitor using OpenCV. From this stage, several vital extraction pipelines have been developed: a template matching pipeline, a template independent pipeline, and a grid detection pipeline. All our pipelines begin with segmentation of the monitor, where we extract the screen from the image and apply image processing on an obtained screen to obtain a front-facing monitor image. Keeping the screen in this orientation improves performance for text detection models that come later on in the pipeline. So, the monitor segmentation pipeline can be divided into three main steps, as shown on the slide. The first is screen segmentation, the second is corner identification, and the third is image warping. We will now explain each step in detail. Screen segmentation was done using YOLO v5. We used the YOLO v5 segmentation model and trained it on the segmentation dataset provided with the problem statement. Good results were achieved with a training and validation accuracy of over 99%. Next, we carry out corner detection of the segmented monitor. Since the default bounding box predicted by YOLO is a best fit polygon, it contains too many vertices to identify the monitor corners in a straightforward manner. We solved this problem by generating a new best fit quadrilateral mask. The predicted mask was first cropped out, blurred to smooth out edge irregularities, and the resulting image was subject to thresholding. After this, contours were extracted from the images, and we used the OpenCV approx polydp function to generate a new quadrilateral mask. The obtained bounding boxes contain exactly 4 points, and this helps facilitate warping in the next stage. The final step in the monitor segmentation pipeline is image warping. In this step, we generate a transformation matrix for the image using OpenCV perspective transform. The matrix, when applied to the image, maps each point on the monitor to another point on the screen such that all points are at the same relative distance from each other as in the original image. This helps us remove perspective distortion in the image while maintaining image quality for text detection later on.
At this point, we have successfully obtained the vivid state and corrected image of the ICO display. The next step is to categorize each vital on the screen according to its relevant category, namely HR, SpO2, respiration rate, HR graph, and BP. For this, we tried experimented with three pipelines and are still experimenting on the fourth. We finally selected the grid matching pipeline, which gave us the most satisfactory results. Firstly, we experimented with the template matching method. We had been given multiple templates of ICA monitors, each having a different spatial position on the monitor screen. We built a custom CNN model to classify the monitor image into what type of template it matched to. After template matching, we tried to build a model that recognizes a vital on the monitor and specifies what class it belongs to. The most obvious features that the model could learn was either the position of the vital in the screen or the color of that particular vital. Learning from the position clearly failed because there was a huge variety in the position of labels, even in the same template, and there was a possibility of the labels often being swapped due to disconnection of a vital from the patient. The color method also didn't work well because the color of the vitals was not same for all the monitor types, and in case of critical conditions, the vitals would change color to red or green. making a color and unreliable learning feature. In the eroded images pipeline, our main focus was to tackle images having some glare or reflection, or if the text and numbers were hazy. We eroded the original images and then subtracted it from the original to get a better image, which we then used to train the model. Shown are some of the examples of the images we obtained after processing. We can clearly see that there is no glare, reflection, or other disturbance in the background, and each number and graph has a distinct and clear boundary. But again, the model tried to learn the color and the position of the label, thus giving a not so accurate results. Finally, as the position and the color features failed, only other features we saw were the neighboring elements around the vital data. For example, the small text like HR, SPO2, BPM, or MMHG, symbols like hearts or lung, and value ranges like 120 to 50 for SR would be given around the vital data. So we decided to label the whole grid, which includes the vital number and the text symbols around it, so that the model would learn these features, which are unique to each individual vital and not rely on the color and position. This overall approach helped the pipeline to be more robust and able to detect vital class even though different templates have a different position or color of the label. Here we have displayed some of the results we got on the test dataset after training.
We also worked on a template-independent pipeline based on neighborhood matching. This pipeline was developed with the incentive that on a clear image, we could figure out the vital data on any type of monitor. We basically had to solve three challenges here. Firstly, locating the text on the image. Second, recognizing the text. And lastly, correlating the text labels with the vital data. Our first challenge involved testing of a wide variety of text detection models to find the best ones for our use case. We tried the models based on the Paddle OCR model zoo developed by Paddle. We tried models such as East, DB++, SAST, and FCE. FCE was the best one for us, which gave roughly rectangular bounding boxes and didn't detect the graphs. For recognizing the text, we tried a number of text recognition models, again based on the Paddle OCR model zoo. We tried NRTR, SAR, and RFL among others. The outputs of some of the models are presented on the screen. Our major challenge here was to detect the slashes between the SBP and DBP values and the brackets in the MAP value. SAR turned out to be the best one for our use case. Now, the main challenge was that of the correlation part. This involved two steps. Firstly, sorting out the bounding boxes by area. As the vital data is bigger on the monitor screen, we would get the bounding boxes corresponding to the vital data. Now we would search for a label around the vital bounding box, which is usually present on the top left or top right of the vital bounding box in the radius of 1.5 times the diagonal of the vital bounding box. The label detected will be correlated to the vital data present. To maximize accuracy on blurry images, we link labels such as SPO2 with text like SP or O2 or PO2. The processing time for this pipeline was over 2 minutes per image. This pipeline is supposed to give quite accurate results after proper training. Now, coming back to the template-dependent pipelines, we had got the bounding box for the vital data, which is passed to the OCR for text recognition. We experimented with a lot of OCR libraries. Paddle OCR was chosen as it was the fastest and the most accurate among competitors we had tested. Keras OCR was taking 8 to 9 seconds per image. Tesseract OCR required specific training for our use case. Easy OCR models were slower compared to Paddle OCR.
Now we come to novelties. We have developed two main novelties for the problem statement: HR graph digitization and monitor emergency light detection. Firstly, we have HR graph digitization. This is achieved by segmenting the HR graph using YOLO, which produced a bounding box around the HR graph. The image was cropped around the bounding box and image processing techniques were applied, consisting of pyramid mean shift filtering, Otsu thresholding, and binarization of the resulting image. The coordinates of each white pixel on the image were recorded and plotted to obtain the final digitized graph. Next, we have emergency light detection. Examination of the dataset indicated the presence of red emergency lights on each monitor. It is possible to detect when these lights are flashing using image processing techniques. We converted the image to HSV space and filtered out the red color from the image. Successive erosion of the image helps remove stray groups of red pixels from the image. By estimating the number of red pixels in the resulting image, it is possible to determine if a red light is currently flashing. We also list some potential future improvements in the points on the screen. Firstly, we can speed up the execution time of the pipeline by using lighter YOLO models or developing our own CNNs. Secondly, generative adversarial networks (GANs) can be used to improve image quality by removing glare and blurriness from the images. Thirdly, we can deploy lighter models for edge devices through which we can add vital extraction capabilities on CCTV, enabling vital extraction from video. Lastly, it is possible to estimate the level of blurriness in images by generating a Fourier transform of the image. Hence, we can separate out high quality images on which inference would be easy from low quality images requiring more processing and sophisticated models, improving the average case running time. We now invite questions from the panel.
Uh, Good job. So good presentation. Actually, like really good job on on doing that emergency light as well. Good observation. So, you had like two methods, right? Template based, and another one was what was the other name? Can you go to that slide? Neighborhood matching.
Yeah, it was the
Yes. So here, can you just talk about this a little bit more?
Yeah, actually, in this pipeline, we first developed we actually found detected the text on the screen. Then we identified the text, and based on that, like if you can see the label of the vital data is actually present on the top left or top right in most of the monitors. So in this, we can actually check for labels around the vital data bounding box in the like in the threshold of 1.5 times the diagonal of the vital bounding box. This threshold was set by us by looking on the images which were given in the unlabeled data set. So based on that, decide we developed this pipeline. So
Okay. So could you also have use a correlation trying to match the graphs with the digits?
No, actually, the graphs were we had a difficulty in detecting the graphs because of the scene text detection models that we had. They were giving false positives on the graphs, so we didn't do that. We tried experimenting with a YOLO model based pipeline on which we detected the graphs, and based on the color of the graphs, we would detect the label. But that wasn't working very well because the graph would change color depending on the condition.
Okay.
also just to add, there were multiple images where the graphs were not available on the image, and some of the images had very distorted graphs, which was very difficult to detect. So because of that, the model would return anything because the graphs wouldn't be detected, and there wouldn't be any output as we are correlating the data based on the graph. So that was the one of the problems with that method.
Okay. This one on the text recognition models, SAR, right? Like you guys chose SAR. Um, how much time was it taking for that? For
Uh,
that stage?
Yeah, actually, that was the part which was taking the maximum amount of time because SAR is made to detect very curved text around the it's a scene text recognition model. So yeah, so that was the most time-consuming part of the approach, and I guess it was taking uh, around 30 to 40 seconds on identifying all the labels, reading all the
Okay.
labels.
Okay. Okay. Cool. Pradeep, you have anything?
Can you please go to the segmentation slide? The previous one, when you're doing the crop. Yes, okay. So for the perspective transform, you need the four coordinates of the image, right? Inside the image. So we want to know like how you are coming up with those four coordinates because YOLO will give you like one crop, right? It's a bounding box. So it will be always going to be a rectangle, not the four coordinates that you want.
Uh, so actually, YOLO V5 provides a segmentation model that is added on top of the base YOLO pipeline. It will give us a polygon that contains just the screen image. So it would
Okay,
not be a rectangle.
yeah, okay. Segmentation means like I'm not getting it. Like what will you getting the output as a from the YOLO model?
From the model, we would get a mask that covers just the
Yes,
screen
yes,
portion.
yeah. So mask will be like in the pixels, right? It's not a code, exact like polygon.
Actually, after examination of the YOLO model, how it works, it actually does create a set of points that we are able to output from the program, and that's how it generates the mask for showing. If you output the results in a text file from YOLO by passing parameters, we get a list of a large number of points. So it actually defines a polygon.
So, what Pradeep was asking was like you get a lot of like points, right? So from there,
Yeah.
like how are you choosing those like 4 points to like do the warping?
Sorry. So to do that, we had to generate another bounding box because it is not possible to determine using heuristic methods or greedy approaches. It's not always straightforward, and there might be some errors in the mass bounding box. So what we did was use approx polydp. It's available in the OpenCV, and it creates a new bounding box around the contours detected in the image within a defined error. Like we set the error as 0.05 times the perimeter of the previous bounding box. So since the image is roughly rectangular, it is guaranteed that the best fit polygon would be a quadrilateral, as long as the mask is sufficiently accurate, which it was in practice.
Okay, so
Okay.
this corner detector will run after the mask, right? Or it will run in the original
Yes.
image.
No, after we get the mask, we perform corner detection.
Okay, good. Okay, thank you, guys.
So, on the so like the next one is also like a image erosion, right? Can we go to that slide? Yeah, eroded images pipeline. Um, can you so this was like used for one specific thing. Like, can you go? Can you talk that? Can you talk about this?
Yeah, actually, on many of the images, there was glare and even reflection due to the polythene attached on top of the monitor screen. So we tried to get rid of that. So basically, we what we did was we eroded the image twice and we subtracted that from the source image. So what we were left with was just the outline uh, of the of the graphs and the data of the numbers. It removed the background and it removed all the glare. Like even in the documentation, we have given a image. We have shown an image doing that. Like I can show you the our submitted documentation actually. If
So when this is used, like, so this is used in conjunction with template matching or like the neighborhood uh, matching.
So let me just yeah. So basically, our main objective after the template matching pipeline was to get features other than the position or color of the label. But because the images were very hazy or glare, had glare or reflection, the I think the model was not able to recognize those SPO2 or heart symbols or such stuff. So what we did was eroded the image so that it would try to learn the features around that and then basically learn those features around it and then give the detection. But when we try to basically uh, train the model, we again saw that the model was only learning because of the color and the position of the image. Henceforth, we basically followed the grid matching pipeline. Our main objective was to get the relation using the SPO2 or the HR small text written around the vital data.
Okay, cool. Thank you. So we can close. Thanks, guys.
Thank you.
Thank
Thank
you.
you for doing your presentation.
Thank you.
Yeah. We can leave it.
Yeah.
Yes, 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 yes.
Okay. Thank you so much.
Just give us a minute.
Sure.
We'll start in 2 minutes.
Sure.
Okay. Yeah, we can start.
Jitesh, just a request. Actually, I believe the Meet has noise cancellation on. That is why the bell sound is like I think it's being cut off. So if you can please disable that.
Um. So like this is like enabled by default.
Okay, like
Let's see.
okay,
Let me see. Let me
sure,
check.
sure, sure.
I don't see any option for to actually take it off.
No problem.
So
I believe the
uh,
bells were audible, right? In even in the last presentation. And
yes, yes, yes. It was
okay,
actually audible.
great. So team 59, you please turn on your mics and cameras, and we'll start in a bit.
So there's an announcement for the team. We'll be ringing a Hi, so there is an announcement for the team. So we'll be giving a buzzer sound at 8 minutes and 9 minutes 30 seconds into a presentation. And here's how the buzzer will sound.
Were you able to hear it?
No. No.
Okay, please wait.
Yeah, now it's clear.
Yeah.
Okay, now you can begin.
Oh. So is my slides visible?
Yes, it is.
Yeah, good morning everyone. Our team ID is 59 and today we are going to present our solution towards the vital extraction challenge. So there are a lot of outdated monitors used in India today that can't read the vital signs digitally and they need to be physically checked for any kind of anomalies. In addition, there is no means to digitally send the vitals to any other device and it might not be cost effective to implement this on a hardware level. So, without the need of an external hardware, the computer vision based approach being discussed can accurately and efficiently extract the vital signs from the patient monitor using only its image. So, digital image of a graphic data is displayed in the images that can also be used to recreate the graph of a particular image using Matplotlib. So first we saw that when we extracted the bounding box of a graph using YOLO technique, there are two type of classes, the background class and the foreground class. So when we draw a histogram for the pixel distribution for the graphs that we received, we observed that also thresholding can help us in order to distinguish the two type of classes. We applied grayscaling and also thresholding to binarize the image. Then we do pointwise operation over the entire image to discover pair xy, where y is the position where the value of pixel is 255. And since we have all xy pairs, we used Matplotlib to draw these graph using the pair of these numbers. So there are a couple of other approaches we have also tried, which are not in our final solution. These includes monitor classification, number extraction via color filter, and contour extraction and digit recognition. So my friend Dhruv will explain in detail what are these approaches
Thank
and these are not in our final solution.
Thank you, Aman. In our initial approach, what we had decided was that we would consider every separate layout and color combination in the monitors and make a separate filter for it. This separate filter or mask will extract the vital from the image, and then we can pass this extracted vital through the OCR to recognize the numbers. But the issue with this strategy is that there are a large number of combinations of the different layouts and colors that we have, and hence making a common filter for detecting a single vital is not possible. Also, there were certain issues with the lighting conditions when the image is taken, and this was changing the color. So this approach was not that feasible. As mentioned in the previous slide, because we had planned to have a separate model slash mask for every type of layout, we had first trained a monitor classifier, which told us which type of monitor layout a particular input image was. This was a CNN model with 4 convolutional layers followed by a pooling layer, then a flatten and dropout layer, and finally 2 dense layers. And we had obtained a pretty good F1 score of 0.98 while doing the classification. But later on, what we discovered was that our detection model was able to generalize pretty well on the different formats of the monitor layouts, and hence we discarded this classifier. Finally, for the digit recognition, we had trained a custom pipeline. What we did was, given a cropped image of the vital value, we first used binary Otsu thresholding to binarize the image. Then we eroded the image to get separate out all the digits, and then applied the contour finding algorithm, which found separate contours for each of these digits. Then using these contours, we cropped the image into the single digits that we had and passed each single digit through a 4-layer neural network that was trained on the MNIST dataset to do the recognition. Once we had the labels for each of the separate digits, we combined them together to get the value of the actual number. This was working pretty well and was fast, but because we did not have a large scale annotated data set, we could not do the benchmarking and get the exact accuracy. Hence, we used a pre-trained OCR technique in our final approach. Now, Manas will explain us the final inference pipeline that we have used.
So thank you, Dhruv. Now I'll be explaining the final inference pipeline. As Dhruv has already iterated over the different approaches tried, I will focus more on the final approach. So basically, as you can see in that image, we have the original image which was directly taken from the data set, and then we detect the bounding boxes and the corresponding labels of that image using a YOLO model that has already been fine-tuned on the dataset. Next, we use optical character recognition to basically pass each of those bounding boxes to the OCR software, which then reads the digits present in those bounding boxes and finally predicts what are those digits. We calculate that the total time that it takes to completely do inference of our entire pipeline is 1.6 seconds per image. Uh, Now I will be explaining each step in that inference pipeline in more detail. So basically, the first step is where we detect the bounding boxes. We can follow two approaches of object detection models here: region-based detectors and single-shot detectors. The family of algorithms which fall in the region-based detectors are the CNN, RCNN, fast RCNN, faster RCNN, which actually work in two stages. Firstly, they detect the regions of interest from an image, and then they pass those regions of interest to a classifier in a regressor, which detect the object and also output labels in that object. Now, the thing is that this is in contrast with single shot detectors like YOLO, which we have used, which predict the bounding boxes along with the class in one single pass. This gives the single shot detectors an edge when it comes to real time inferences in which we are actually interested. Moreover, in our approach, it is important to note that we don't really use the YOLO model on the cropped images directly. We can actually input any type of image where the monitor is a small part of that image. This is because YOLO is size invariant, and basically it can generalize well even to uncropped images. Because this is an important discovery as it prevents us from spending that time into first extracting the monitor out of that image and then further processing, and it can save us much a significant time on inference of that image. Next, we come over to easy OCR of our pipeline. The easy OCR solution basically is a very flexible and modular solution as it provides us two APIs that detect and recognize. In detect phase of the easy OCR, we can it basically allows us to detect the bounding boxes on that image. And in the recognize phase, we will recognize the digits in that bounding box. But the thing is that we did not really use the detection part of the easy OCR. Why? Because in easy OCR, they only use the RCNN region-based detector models, which are slow, and we replace it with our own custom pipeline of YOLO models of the YOLO family, which are actually very fast. We have used YOLO V7. Next, in the recognition phase, as can be seen below, we use a LSTM-based recognizer, which converts the initially drawn features from that image into a sequence of features and feeds it to the LSTM. And finally, this LSTM model can predict what exactly is the digit in that image. I would like to conclude our presentation by saying and emphasizing that YOLO model actually does not require us to do and waste much time on pre-processing steps, and it can generalize well to different variations of zooming, lighting conditions, etc. And we have tested that ourselves. Moreover, we have reduced the time down to 1.6 seconds, and even further, we can tweak it by doing batch processing and parallel programming. So I believe that it is now time for my teammate Aman to show us a working demonstration of our code. Yeah, sure. So as you have pointed out that there is a slight bit of error in our code. So the bit is that our code throws an error when nothing is detected in the YOLO part. So that is an error on our side, and we have simply corrected it by adding a try except block. And if nothing is detected by a YOLO part, we just output a simple empty image. So the error can be rectified. The error that you have mentioned can be rectified by adding a simple try except block, and this is an error on our part. So our code just works fine. Thank you. We conclude our presentation, and we are now open to questions.
Okay, so you have made a custom OCR, right? Where you are like using Can you go to that slide, that custom here we have made?
Yeah, sure. One second. Yeah,
Okay,
this one.
so yeah. So you are eroding those images and trying to like separate out the digits.
Yeah.
So my question here is like, say you said like you have like experience that even in different lighting condition, your model is working correctly, right?
Yeah.
Yeah. So if you are using custom OCR, so what happens is like when the lighting condition is like not proper, so what happens is like blur image is slightly blurred. So one digit will go into another digit. So
Yeah. So
then you can't like separate out those digits because like it will not be like a one separate digit but union of the digits. So in that case, how this OCR is working?
So we have developed this OCR by a iterative process. Suppose the digit are mixing too much, then we apply eroding of 3 cross 3 kernel, 3 cross 3 kernel at a iteration of 1. If suppose this is SBP, we have applied it for SBP. We are interested in detecting 3 digits. So we have iterated multiple times, and we have increased the number of iteration. And
So
if
my question is, it won't give you three digits. It say
yeah,
suppose like if you go into last slide, right, where you have like presented that monitor part, right? Yeah,
where
previous one. Yeah,
yeah.
this one. Here you can't get like 96 out of there. So if
So
see this image is like clear, but like say there is some lighting problem, then 96 won't be like two digit. It will detect as a one digit only because
so
9 and 6 will be merging together.
So first we have applied a 3 cross 3 kernel and try to erode the image and try to detect 9 and 6 individually. If we know that it is heart rate. So if we are not able to properly segment out 9 and 6 and our MNIST classifier is not giving a proper decent output, then what we did is increase the kernel size to 5 cross 5 and then again tried. And then we again increase the kernel size to 7 cross 7 and try to segment out the digits into 9 and 6. So if finally 7 cross 7 kernel fails, we output dash.
In that case, it won't like output anything.
It will output if it is able to erode the image in those particular iterations. We have eroded it with a 3 cross 3 kernel. If that works fine, it outputs it. We have tried 5 cross 5 kernel. If that even if 5 cross 5 also fails, then we have tried 7 cross 7 kernel.
Okay. So another question is like you are not segmenting the image, monitor screen part, right? So
Yeah.
say suppose example you are seeing here, there is inside the corner of it's written MP20. So some monitor will have a large digit, or sometimes in the background also there is a large digit. So how you make sure like YOLO is not detecting that one? Say suppose like bed number 23 is there. So there is a like a slight discrepancy because bed number is 23 is not a part of the monitor.
Yeah. So Manas will answer this question.
Yeah, sir. So basically, we were relying on, we have tested ourselves on different number of images, and we found out that even after it is overlapping, our YOLO model is robust to those small variations.
Yeah,
Uh,
but it's
we,
okay. Like I'm not asking for overlapping. So what I'm asking, you can see in the background there is a one box, gloss box. It says like polymed. Inside that in this image it's not clear. Inside that after that box you will see a board over there, and there is a board. It has a big number. It's written the bed number. So there are many images that you will find like that kind of board over there. Say suppose like bed number 23 is there, so how you will know that it's a respiratory rate and not the bed number?
Yeah. Actually, the point you mentioned is valid. But what has happened is because the monitors follow a certain coloring convention, it has learned this color, associate the color with the value as well. So it will not recognize any 23 as a respiratory rate. It will also try to see the color and the location of the uh, relative location of this number. So that's why this cropping is like work, like without even cropping, it is able to get the right numbers maximum number of times. Now, yeah, it might happen that in a slight case where the number is exactly in the same color and same size, it might work, but in most of the cases that will not happen, because it has not just learned to detect the numbers, but it has associated these values as the relative position and the color of the number as well. Because we even tried this on some other monitors, which like whose format was not present in our training data set, and it was able to recognize at least the main values such as the heart rate and SpO2 even in those monitors, because of these certain patterns that it has learned.
Okay. 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 Thank you, guys. Thank you. Um, Chidesh, you can click close this.
Yeah, yeah. Like we can continue on to the next one. Good afternoon, Team 61. So, good afternoon. So, wait.
Hello.
Yeah.
So there's an announcement for the team. We'll be buzzing you at 8 minutes, and after 9 minutes and 30 seconds into your presentation, as the warning bell, here is how the buzzer will sound. I hope it is audible.
No.
Sorry, we were not able to
No, sir.
hear it.
Just
Hello.
is it audible now?
No.
No, sir.
So there was a slight sound.
We'll try to play it again. Just a minute.
All right.
Uh, just a minute. Just a minute. I think there's noise reduction. Manage it. Just please wait for a minute.
Yeah, got it. We can hear
Yeah.
it now.
So now you can begin the presentation.
All right. Aman, share the screen, please. Okay, so can we start? The
Yeah, please start.
All right. Okay, so good afternoon, everyone. Welcome to the solution presentation of Team 61 for the Vital Extraction Challenge. Following is the overview of our presentation deck, objective, intuition, our approach, models used, our novelties, and we display a few of our results. As we all know, the objective of the PS was to extract vitals like SpO2, heart rate, BP, and respiration rate from raw images of the monitor screen, and also digitize the graph, the HR graph, right? So while approaching the solution, our intuition was to initially capture a clear image of the monitor screen and then proceed with further processing. Thus, we bobbed and enhanced the monitor screen images from raw images using a novel approach by combining two powerful techniques of semantic segmentation and object detection using YOLO, about which it will be very clear in the further presentation. Then OCR was applied to extract the numeric vitals, and object detection coupled with contour detection was used for HR graph digitization. The deep learning models used in the process are listed on the slide, namely YOLO, UNet with encoder backbone of ResNet 34, ResNet 50, and Padalosia. For implementing the object detection on the extracted monitor screens, we manually labeled nearly 1600 images using MakeSense.ai tool, 400 images for each class of the monitor layouts. So the following is the snapshot of annotating images. Right. So as you can see, we are not labeling our objects based on their location of that objects, but rather our objects are context sensitive due to the surrounding strings and symbols around the actual numerics of the vitals. Right. So after training our models, we employed the following pipeline. As I mentioned, we combined YOLO and UNet outputs along with some warping, which will be cleared later. Then the extracted monitors were classified into their respective layout classes with the help of ResNet 50 model. And following this, a layout-wise YOLO object detection model was trained and used, and further text recognition and HR graph was done using objects extracted from those monitors. Over to Pulkit.
Okay, so the very first part of our pipeline is to extract the screen of the monitor, which is the only meaningful area of the image. For this part, we have implemented an intricate combination of semantic segmentation using UNet in conjunction with YOLO to extract the exact screen cutout. We have used the UNet architecture with ResNet 34 encoder architecture using transfer learning on the dataset provided by the Cloudphysician company itself. During our experiments, we also observed that using grayscale images for training gives more accuracy than colored images. This was because of some ad hoc lighting situations. YOLO, okay, so we have used YOLO V7 tiny model, which has around 6 million trainable parameters for fast and accurate inference. Now the YOLO model outputs bounding boxes for the screen in form of perfect upright rectangles. But we know that the screens might be tilted based on different camera angles. So here, semantic segmentation comes into picture, which gives us output in form of masks. Now we have a problem with only UNet model. We are calling this problem as we faced as the multiple corners problem. Now we take the predicted masks from the segmentation model, which have hazy and unclear edges, and we process them to estimate a polygon. We use the coordinates of the polygon to warp the tilted screens to obtain rectangular cutouts, which appear as if the photo were taken right from the front. Hence, we are changing the perspective to obtain better results from further applied OCR models. With an IOU, that is intersection over union score of greater than 0.9, the segmentation model was great, but even slight inaccuracy in mask prediction, for example, a certain erratic bulge in the mask or a small empty area inside the mask, resulted in more than 4 corners getting detected when a polygon was approximated. And due to this, the warps were unsatisfactory in around 43% of the images. So basically, the task at hand right now is to identify the 4 best corners from all the detected corners of the polygon. Now, one thing we have to realize is that straightening of images very much is essential for extracting the graph, because in a tilted image, the graph kind of appears diagonal and it appears like it has a trend kind of something. So next slide, please. Our novelty in screen extraction. So here comes the solution to the more than 4 corners problem. Now, at this point, we had the approximated polygon determined from the UNet masks and the bounding boxes from the YOLO V7 model. We use the corners from the YOLO bounding boxes to estimate the exact 4 corners with high confidence from the multiple corners of the mask. Now here I'll try to show you the results that we obtained from the procedure that I explained before. Here you can see the input images in the left. The image in the upper right corner shows the cutout obtained from the YOLO's bounding boxes, and you can notice that it's slightly tilted. The image in the bottom right shows the rectified cutout, which has been obtained via a combination of segmentation mask, YOLO bounding boxes, and image warping. Now that moving on to the next task, we were provided with 4 different types of monitors in the classification dataset. We used a ResNet 50 based classification model to deal with this part of the problem. And as you can see, we have 4 different classes with 250 images each. And from here onwards, I hand off the presentation to Shreyas.
Okay, so once we find out the manual annotations using the MakeSense.ai website, we created two types of YOLO models. One was for screen extraction from a far-off image of the monitor, and the other was for component detection inside the screen. Now, for the screen extraction YOLO model, we had the final layer as only one class, which basically gave us the output of whether that screen existed in that image or not. And for each of the monitor-specific YOLO model, we had 5 output classes, that being HR, BP, SpO2, respiration rate, and the HR graph, which is indicated by HR_W. Now, once the classification model was fed the monitor screen, it gave us the monitor screen type and then that particular YOLO model for that monitor type which was trained was used to predict the component bounding boxes. The output of the YOLO, which were those five images, were fed into the OCR function such that we find out the final resultant dictionary. For the OCR, we used Paddle OCR. Why we used it is because it was giving us fast and accurate results. And the only problem with Paddle OCR is that what it does is that it finds out the all the text present in that image and creates bounding boxes around it. Thus, we were getting very unnecessary text such as /min or HR or whatever was written around the number. So what we used as an algorithm was that we found out the bounding box with the maximum area, which by manual inspection gave an analysis, we found out that it was invariably the main number which we finally wanted to extract from the smaller image. So that was one filter. The next we did we applied some regex to get the sanity of the recognized text, and we also reduced false positive using non-max suppression. Now, for the graph digitization, what we did was once we find out the extracted HR underscore W image, we converted it into binary, which was basically black and white, and then we used contour detection. Now, contour detection, what it does is that it finds out the change. Like there were two lines which were detected. One when the black screen was converted into was shifting into the line of the graph, and then the other when the line was shifted into the black screen. So we took the mean of those two to get a singular input line. And for all the contours present in the image, we took the longest contours, thus resulting in a single representation of the HRW graph. Now I'll talk about a little of the future innovations which we thought of. One was optimizing the filters of the Paddle OCR and fine-tuning it such that better results came. And two was is the time up?
You can continue.
Okay, the second was to get a full YOLO model such that we can reduce the model inferencing time and remove the classification component totally. I'll just move on to the final results ones which we got. So this as you can see the
There
Hello.
is some network issue, I think, from the screen share. The final results are not visible, right?
I can present my screen if required.
Yeah, it's just one slide. Yeah, got it.
Yeah, so here is the segmented monitor screen which is going into the classification model. Let's say it gives us the output that it belongs to class 2. Then the YOLO object detection model for class 2 works on it, thus resulting in these 5 images. Out of these 5, 4 of them go into the Paddle OCR, thus giving us the numbers of the BP, HR, SPO2, and RR. And the HRW goes into the function which digitizes the graph. The results can be seen in the next slide. Thank you. This ends our presentation.
Pradeep, you can ask.
We are
I'll go
open for
next.
questions.
Yeah, sure. So for digit classification, right? How do you are classifying those digits?
Yeah, so we have object detection, right? So there's YOLO trained for the monitor screen. So in the YOLO, there are multiple classes. Like this is an HR object, this is an RR object, this is the SPO2 object, this is the
Okay,
HRW
so you
object.
are yeah, you are using YOLO for classification also, right?
Yeah, right.
Yeah. Which model you are using for that one?
YOLO V7.
V7. Okay. What is the size for it?
Tiny.
What? Oh, sorry, I didn't get it. Oh, which size?
So we are using the YOLO V7 tiny model.
Tiny. Okay. So it might be like a case you have like come across. To spin it don't have like specific color. Right? Sometimes it's only white, and the digit appears in the black. So in that case, how you are like classifying those?
Sir, so basically, what we saw was that, like he has mentioned in one of his slides, beside the HR number, the main number, there are small contextual information which is given. Like, for example, the heart with the min, the HR word itself, and things such as that. So once we annotated the images manually, we trusted YOLO to find out those contextual details beside the main number also, such that it can classify it well. We are not just taking only that part of the 85. For example, you can see in this particular case that for the BP there are multiple things written across it. For the HR also there is a heart and slash min and these details. So we trusted YOLO to find out this. We use these annotations which were manually done by us, not the ones which only had that number there in that image.
Okay. Okay. Good. Jitesh, you can ask.
So, like this, like the monitor classification was only trained on four types of monitors.
Right, sir. So the classification data set provided by Cloudphysician itself had four classes. I think those were BPL, Ultra Primes, and Neon something. So these four were the different types of monitors that we saw existed in both the classification and the unlabeled data set, both provided by you. So we considered those four as the monitor types. We could increase the monitor types, or we could move to the to a new innovation based on the test data set given to us, that we create one final YOLO, or we move do that classification step. So there are two approaches that we could follow.
Okay. 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 Yeah. Cool. We can close this. Thank you.
Right, sir.
Thank you so much.
Okay, thank you so much.
Yeah.
Sir, do we leave the meeting?
Yes, yes, sure.
Yes. Yes.
Yes. Thank you. Nice meeting you.
Thank you. Just.
Hi team. Hello.
Hello, good afternoon, sir.
Good
So there's an announcement for the team. So we will be buzzing in at 8 minutes and 9 minutes 30 seconds into your presentation as a reminder. Here is how the buzzer will sound. You can start now.
Also, Team 17, if possible, please turn on your cameras. Thank you. And you can begin your presentation.
Shall we start now, sir?
Yeah. Yeah. Please start.
Yeah, thank you. Good afternoon, panel. We are Team 17 with the presentation to our problem statement as given here. We use the given data set provided by the company. Our our basic approach is first to extract the screen area from the image, detect the vitals in it, and use the OCR directly to identify the characters. Screen extraction. The only useful part in the image is the monitor screen. This is a visual representation of three different methods we used for screen extraction. Our first step was very rudimentary approach. We used ResNet 18 based regressor to predict the coordinate of the four corners of the monitor, but the prediction were inaccurate, so we moved on to the different approach, instant segmentation, using the mask RCNN to obtain the mask of the screen. But the masks were irregular in shape, so we decided to use only bounding box around the screen. Hence, we ultimately went for YOLO V5 M6 model. After performing detailed data analysis, we use the following data augmentation to make our model more robust to different types of images, such as horizontal and vertical flipping to avoid position-based learning. For example, we observed example position of HR, which was not specifically present on the particular screen, and we change the saturation to get robust even on the washed out images. And we also added blurring and salt and pepper noises to mimic the dust. As you can see sample images from the argumentation here. The issue we faced after training YOLO only on the label dataset was that it predict multiple instances of the same class in an image. Thus, to improve the prediction, we used semi-supervised learning on unlabeled dataset via pseudo labeling. This was our novelty. There is a small typo in our slide. We initially trained our model on 2000 images, not 1000 images. We used the model for predicting 500 unlabeled images and used the predicted label of these 500 images along with the original 2000 images to train our model again. We continued this process till our training dataset grew to 4000 images, which improved the accuracy of our model and reduced the false detection. As you can see, the whiteboard is no more classified as the screen.
Moving on to vitals detection for using object detection. We started with using a simple classifier for 4 classes of the images and followed by different detectors for each of the class. You can see the result in the below image. The bounding box over SBP and DBP is missing. The possible reason for this error might be that uh, only few images, 20 to 50 images, were only available for training each detector, which is frankly quite low. For improved results, we moved on to using a single detector for all the classes, even without using a simple classifier. The results improved, as you can see in the top image. Still, the SBP bounding box over there, the image is not perfect. For even better results, we moved on to using different detectors for HR graphs and vitals, which were specially trained using pseudo labeling. The results can be seen on the screen. Moving on to character recognition, we first implemented easy OCR, which gave unsatisfactory results. Hence, we moved on to using Tesseract OCR. But Tesseract OCR doesn't give good results on small and blurry texts. For example, it frequently detected character 4 as capital A. We moved on to using paddle OCR, which works fantastic for noisy and small images. One benefit that paddle OCR provides over other methods is that it works well for tilted, rotated images. To make the detection even more robust, we added a 50 pixel padding around the detected boxes. And to take care of the characters like brackets and slashes, we added special care in the code that we have.
Moving on to the part of the HR curve digitization. Our input here is an image that consists only of the HR curve, and the output is a final plotting of the samples of the graph at various points. So we experimented with different techniques and we finally settled down on our very novel approach. So our first rudimentary approach was to threshold images based on the pixel intensity. For this, we specifically used the green channel of the image since we observed across all images, the HR curve is of a very stark green in color. However, this was not possible because it is not possible to generalize a threshold for all images, since there are many images which are highly whitewashed and have low saturation. So it is not possible to threshold based on a specific threshold. Second was a kernel-based search algorithm that scans nearby pixels and then it moves in the direction of the next highest intensity of pixels. This did not work well because there are many regions where there is high overlapping of the text and the graph. So in this case, the kernel moves into the text region and it sometimes gets stuck in an infinite loop. Also, a major problem is there are very evident discontinuities in the graph, and this method was not possible or feasible in these cases. So we settled down on our final approach. We fine-tuned a pre-trained YOLO V5 model with images that were manually annotated by us, annotated by making boundary boxes around unwanted text and symbols that we want removed from our final curve. We used this model to then detect unwanted symbols and text and black them out from our image. And then we thresholded and binarized the image and found contour maps for the finally obtained masked image. These contours were then sampled and plotted, and that is how we obtained the final HR curve. These are the visuals of all the steps that I just explained. Now, I will just present a final pipeline which is a summary of all the models that we used up till now. This is a final overview. This is the structure of our entire model. Next slide, please. Yeah. So the first image consists of a sample of a data set, sample of an image of a data set. The next image contains a cropped out monitor of the cropped out monitor of the screen. The image on top contains the vitals extracted and bounding boxes made around them. The output we get is a Python dictionary, which contains the class label along with the value that our model has predicted. The image on bottom contains the extracted HR curve. The image on the right of that is the very evident depiction of that, and the bottom is the plotted contour samples. So to summarize the results, there are two major techniques that have been mentioned before. So the very first technique was screen extraction with masked RCNN, which used a single YOLO V5 network for vitals and graph that gave a 90.21% accuracy in 11.57 seconds of average inference time. So we use an improved technique wherein we use screen extraction with YOLO V5 M6 and use two separate YOLO networks, one for vitals, the other for HR graph. This gave an improved accuracy of 93.72% and an average inference time of 2.26 seconds. This depicts a novel approach that we were able to obtain a pipeline that is thin, lean, and lightweight, which provides a very high accuracy. Also, for the accuracy testing, we had separated a randomly chosen set of 1,000 images in the beginning. This test dataset was not exposed to our model anywhere in the training part, and hence it provides a very robust and accurate testing score. The inference time of the model was calculated on Colab CPU. There are some areas that we could have explored, but we did not proceed to because of time constraints. These scopes of improvements are A, using spatial transformation networks to get orthogonal layouts from screen extraction, using vision transformer-based detectors for better accuracy, combining pseudo-labeling with consistency training to improve results, and experimenting with better LR schedulers, optimizers, and their parameters. These are the references that we used, some of the references that we used. Thank you very much for your time. And the appendix contains structures or architectures of various models that we used in our pipeline.
Okay, thank you. Can we go to the character recognition slide? On that, so you guys are told you have used paddle OCR, right? Why do you think it gave accurate versus distract and easy OCR?
Actually, Tesseract OCR was not good with the small and blurry text, and because there were very instances where the bounding box predicted by the YOLO model was very small, and and we tested both the Tesseract and paddle both, and the paddle gave better, and it also mitigate the problem of slashes. It did not falsely detect the slash as one, which was a plus point for using paddle OCR.
Okay.
Okay, I have one question. So you are doing data augmentation, right? So where you are using blurring and noise.
Yes, sir.
So is there any specific reason you are using salt and pepper noise?
Yeah, it mimics the dust in the pathway of the camera and the screen. As you can see, during the night time, the dusts are very prominent because the dust can be easily get into the light and obstruct the screen. That's why we use the salt and pepper noise.
Okay, but this salt and pepper noise, how you are using it? It's not like a granular size you are using. You are using a pixel wise, right?
Yeah.
So it's not going to mimic dust, but it will pull your model to train it on a different type of data distribution.
But we are using just for up to 5% of pixels.
What I'm asking is any specific reason why are you using that?
We just thought of it would act as dust in the pathway of the image.
Okay. Perfect.
Or one benefit it might provide is it might make our model more robust to uh, uh, other any different data type, data distribution that we might see in test data set. For example, just the way that dropout works, maybe.
Okay. Good. Thank you, guys. Yes.
Okay. Thank you.
Thank you.
Thank you. We can close this. Thanks a lot.
Thank you, sir.
Okay, we'll like to start. So
Hi, team. Just a
we'll
minute.
start with presenting the slides.
Hi, just a minute, please. There's an announcement for the team. So we'll be buzzing you in after 8 minutes and after 9 minutes, 30 seconds into your presentation. Here's how the buzzer will sound. As a reminder, you can start now.
Right, so we'd like to start, if that's okay.
Just a minute.
Yeah. Samit, mute. Yeah.
Yeah, please start.
Okay, so hello everyone. This is the Vital Extraction Challenge as explained by Team 53. So moving on, the problem statement assigned to us was to extract vitals from the ICU monitors and digitize
Hey,
the heart rate graph. I'm glad
excuse
to
me.
say that we have achieved both, and in the coming minutes, we are going to
Excuse
explain
me.
how we did that.
Hello?
There is a echo.
Here's the pipeline of our solution. We take the image as input, and we first segment
Guys,
out the
guys,
screen.
guys, excuse me. Sorry to interrupt you guys, but both of you have kept your mic open and you're in the same room, so there's echo. I repeat, request one of you to turn off your mic and please start again. We'll start the timer again. You can start from the beginning. If you
Okay, you would like for us to restart?
Yes, because if you're in the same room, please both of you should not switch on your mic as it causes echo and the judges
Yeah,
cannot
yeah.
hear
Okay.
anything.
Very sorry for the
So you
inconvenience.
can begin again. We'll start the timer again when you're ready.
So we'd like to start in 3, 2, 1. So hello everyone. This is the Vital Extraction Challenge as explained by Team 53. Moving on, the problem assigned to us was to extract vitals from ICU monitors and digitize the heart rate graph. I'm glad to say that we have achieved both, and we are going to explain how we did that in our next few moments. Here's the pipeline of our solution. We take the image provided as input, and we first segment out the screen. Then we take the mask and approximate it to a quadrilateral and use its corners to apply a perspective transform. Finally, we take the processed image and use an object detection model to determine the regions of interest. We then pass each of these regions through an OCR to produce the results. The total time taken by our pipeline on average is only around 400 milliseconds per image, and now we are going to explain each of these steps and approaches involved in detail. The first task involved is pre-processing using segmenting the monitor screen. Our first approach was to use image preprocessing to obtain the screen. We exploit the lack of green and red channels on the monitor to apply a Brown's filter threshold and remove the noise surrounding the monitors, and then get the required contours. However, this approach fails to obtain corner points required for perspective transform reliably, since in various use cases, we have flashing emergency lights involved, and in dark image perspectives, dark lighting, which make it unsuitable for segmentation without some instance of machine learning. Hence, we did not use this approach in our final pipeline. Our next approach was to exploit the fact that the monitor is Our next approach was to exploit the fact that the monitor is always quadrilateral to get the corner points to train on object detector. We take two bounding boxes to train the object detector on each of the opposite points of the segmentation dataset provided to us. However, again, it fails to detect correctly in cases where or image is kind of already segmented, and in some cases where the corner is absent and the image is a really close crop up. And hence, we have to discard it in favor of classical segmentation for better accuracy. For segmentation, we tried a variety of architectures. For example, segformer, which uses transformers, and for semantic segmentation, and YOLO V8 for instance segmentation models. Segformer had a higher accuracy on average, but its inference was slow, while YOLO hit the sweet spot between time accuracy trade-off, and for that region, we chose to use YOLO V8's and segmentation model in the final pipeline. Lastly, we use the mask generator from the segmentation process to get a quadrilateral. We use contour approximation to get the points required to do a perspective transform. Here, as you can see, we are using the, we are color-coded the initial and final points, and the corners of the rectangle are the final points, which we apply on the screen using affine transformations. Now, moving on to the detection.
For the detection of vitals, we tried various detection models like RetinaNet, various transformers, and different versions of YOLO. We found that the best speed accuracy trade-off was in YOLO V8, which gave excellent results on the classification dataset. But when we tried it on a custom dataset we made from both classification and unlabeled dataset images, we found it to be only 74% accurate. So we had to find a way to use the unlabeled images to improve the accuracy of our model. Our initial approach was to try semi-supervised learning. We took inspiration from a Google research paper called Fixed Batch. We took 2 copies of the model, trained on the labeled classification dataset provided to us, a student and a teacher. We made the teacher label all the images with confidence thresholding to generate pseudo labels in our unlabeled dataset, and then train the student with the labels generated by the teachers on the augmentations of the same pictures. After training for a while, we transfer some of the student weights to the teacher and repeat the whole process. We did this for 10 such passes. However, we did not find much of an improvement. With semi-supervised learning out of the picture, we had to leverage the unlabeled dataset for adding images to our classification dataset. Since labeling 9,000 images is impractical, so we implemented the SCAN algorithm, which stands for semantic clustering by adopting nearest neighbor, to classify the unlabeled data set into semantically meaningful clusters. This was done by first using an encoder to make embeddings representing the high-level features of the images. Then we found 3 nearest neighbors of the feature vectors made by the encoder. Finally, we trained a clustering model to maximize the inner product of the nearest neighbor we made. We made 40 classes from this method and sampled these images and manually annotated to our primary dataset. This enhanced our accuracy from 74 to 96% on our custom dataset. Next in our pipeline is the OCR for extracting the vitals from the detected targets. One of our first approaches was to use the fact that in our case, the colors in which the vitals are displayed are really bright on a dark background. So by image thresholding, we get a clear binary image of the vitals, and by using contours, we can separate each digit and read them. We read the digit by using match shape algorithms. This approach was fast, but the main hurdle was images with glare, where simple thresholding fails to give accurate counters reliably. So we needed a more robust solution, and the answer was pre-trained OCR models. These were the few OCR models we tried. However, they gave a high inference time, which was not affordable since we needed to read 6 numbers per image. After some deliberation, we settled with Paddle OCR for our pipeline, mainly due to its flexibility. It allowed us to reduce the time in favor of restricting some of its functionality. We managed to reduce the time required to 10 milliseconds per vital. Even after dropping the inference time, the model's accuracy was still up to the standards. After this, we discovered that the OCR had some issues with some digits and was reading brackets in the case of MFP. So we decided to implement some manual checks to correct the reading. This helped us increase our accuracy even further. Now moving on to the bonus task. As you can see here, we had given an example of where we obtained a graph from the pipeline on an HR wave by using the thresholding and time series plotting. Thank you very much. Now we would like to show a demo of our inference.
As you can see, this is our final submission. As you can see, this is our final submission here.
Yeah.
I've
Okay.
already made all the imports required. I've already loaded all the model weights. Now I'm going to choose a completely random image from the unlabeled data set you sent us. And I'm going to show you the results. As you can see, HR 96, SpO2 96, RR 13, and that's the only numbers we can detect. And it took around 284 milliseconds plus minus 5.51 milliseconds. I'll take another image just to show that this is not a fluke. We really are getting these times. As you can see, HR 84, SpO2 95, DBP is 75, SBP is 123, RR is 11. Time again 304 milliseconds plus minus 13.9 milliseconds. Thank you for listening to our presentation. Thank you for seeing our demo. Thank you.
Okay. So, you guys have like done used like a detection for like for detecting the digits, right? So, like, can we go to the slide?
The slide.
So, yeah. So, like, so here, like, the detection is happening. Like, how is the mapping to the vitals like happening?
We we just train the model on the object detection of RR, HR, and SpO2 and DPP, and it worked really well.
Okay. But like really good thing with like the inference time. So, uh, yeah. So can this one like so you guys also like settled for like parallel OCR, right? So when you were like testing out like the other like OCRs, like what like problems that you guys came across?
Uh, so, sir, when we used the other OCRs, the inference time was quite high. The thing with parallel OCR is it's extremely flexible. You can only use a recognition model of the parallel OCR. You can only use a detection model. So in this case, it already detected the digit. So we just ran the recognition. And we used the lightest model they had since the digits are very regular. They're pretty much printed. So we just use the recognition model, the lightest model available. So it gives extremely fast results. Like the results are like around 8.54 milliseconds as per pattern.
Okay, cool. On the graph digitization part, like so, can you talk about that once again?
Uh,
Just give us a moment.
Okay, so for the graph digitization, we actually first applied thresholding to convert the cropped image into a grayscale image and then further into a binary image. And finally, we extracted those pixels of the HR graph which have white values and then stored them in another array and finally plotted a time series plot for that particular data set. And then in order to get rid of those words around the HR graph like adult and monitor so that the graph doesn't get distorted, we chose the longest content component for that particular graph and then cropped out those words to finally get only selectively the graph of the HR, only selected the HR graph.
Okay. So like when you're like doing some like thresholding and all, like you'll not get like this continuous points, right? Like so how did you come to this like very fine continuous points, which is like shown on the slide?
Okay, so after we apply thresholding for time series data, we've chosen those pixels with white values, right? And finally, we took a mean in order to get those kind of tables. And then we appended that into an array.
Okay. Pradeep, do you have anything?
Yes. For OCR, right, you are using rule-based approach. So what are the rules that you are applying?
So what happened is that sometimes there are brackets detected. So
Okay, so I see like one is bracket, either it's a parenthesis or curly braces.
Yes.
Is there any other rules you are applying for that?
Yes, sir, we are. What we are doing is sometimes we tested it on a lot of images. We found that sometimes it detects the 7 as a T. So we fix that as well. Sometimes it detects a 4 as an A. We fix that as well. Then in some cases, like the SPO2 and RR get flipped because in a lot of the images, like SPO2 is tinted yellow. The RR is also tinted yellow. So yeah, sometimes they get flipped. So we made a check for that in case like SPO2 and RR, like if SPO2 is greater than RR, then there have been most likely flipped. Like it's an almost impossible case when the SPO2 is 18 and the RR is around 80 or so. So we just flipped those values. And the accuracy did improve. It improved by like 3-4% from that alone.
Okay, so for 7 and T, right, okay, that can be like understandable, but like see, sometimes what happen is like I is interpreted as a 1, right? So how do you like coming up with this notation, right? So it's a 1 or slash or I.
So, yeah, for the slashes, there is not much we can do. Like if DBP is greater than SPP, in that case, it has read the slash as a 1. We did take checks for that. Like suppose if SPP was 147 and the DBP was actually somewhere around 91, and the slash was read as a 1. In that case, it would be 147 and 191. We took checks to remove that 1, like from the DBP, because in that SPP is less than DBP is an impossible case.
Good job noticing that. Okay. Pradeep, do you have anything else?
No, Jitesh, you can continue.
Okay. So thank you guys. Like we will close this. Thank you.
Thanks a lot, sir.
Thank you.
Hello.
Hello, good morning.
Hi team, there's an announcement for you. So we'll be buzzing in at 8 minutes and at 9 minutes and 30 seconds as a reminder. Here is how the buzzer will sound. You can start now.
Okay, I'm presenting my screen. I hope everyone is able to see my screen.
Yeah. Please go on.
Yeah. Good evening, everyone. We, members of Team 55, are here to present a solution to address the problem statement given to us by Cloudphysician. The problem statement revolves around extracting the vital information from the monitor present in the hospital rooms. So we put forward a 3-stage pipeline, which is as follows: monitor segmentation, vital detection, and vital recognition. We recorded an inference time of about 0.6 to 1 second for our approach. Our proposed model pipeline runs as follows. We take an input image which contains monitor and vital information inside it. Then we passed it via a segmentation pipeline, which generates the monitor mask for that particular image. Then we correct its perception using some OpenCV perspective transformation technique to convert it into in bird's eye format. Then once we got the bird's eye form of the monitor, we passed it to a vital detector to detect the vital bounding boxes associated with its class. Once we get the detected bounding boxes of the vitals, we passed it via an OCR engine. We using paddle OCR here to detect the text inside each bounding boxes. And in our pipeline, we able to digitize the HR graph as well using the Webplot digitizer. Our complete approach took about zero point 0.6 to 1 second on CPU. So let me take you to our first stage of the pipeline, which is segmentation. We are using an encoder-decoder based UNet architecture for semantic segmentation. We have 2000 label data, which we have divided into 1800 train and 200 validation split. Also, we have 7000 unlabeled data with us. So we are trying to leverage that unlabeled data set by employing a semi-supervised based semantic segmentation approach. On top of that, we are using some novel augmentation technique like RAND augment and LR scheduler, whose performance improvement you can see in upcoming slides. So this is the framework of our semi-supervised segmentation, which we have divided into two parts, labeled section and unlabeled part. For labeled part, we have the ground truth mask. So what the model and loss is focusing on is to make the predicted mask as close as possible to the ground truth mask. So via supervised cross entropy loss. But in unlabeled section, we only have the images, not the ground truth mask. So we are adopting a technique known as UDA, unsupervised data augmentation, which is used by Google for image classification, but we are employing it here for semantic segmentation tasks. We pass an original input image and a proxy of it through augmentation library by employing RAND augmentation technique, which differs only in the color perspection, not in the geometrical transformation with the original image. Then we fed both the images, augmented and original one, to the model and makes the model to focus on the consistency of both the masks. Like we force the model to predict the same mask for both of the image as they are only differ in terms of their color perception. In that way, we are leveraging the unlabeled domain of the images to make the model more robust and generalizable. Now comes the question, like why we are using segmentation and why we are using even semi-supervised technique. So the question lies in the fact that most of the monitor images are not rectangular in size. So if we are employing detection here, maybe the bounding boxes which we are getting is not giving the proper perception for employing in the further pipeline. So we move to the pixel level segmentation for better accuracy. And on the top of that, we have unlabeled data. So we are adopted semi-supervised techniques whose results you can see in the third column of the image itself, that the masks which we have got using the semi-supervised one are more consistent and accurate compared to the supervised alone. Now, this is our segmentation pipeline in general. Like input image is passed via UNet and it converted into a bird's eye view via perspective transform. This alone pipeline took about 0.4 to 0.6 seconds on CPU. These are our like matrices after we got mean in IOU score of about 99% on train and well both, and loss almost converging to 0. Now, once we extracted the mask, we have to rectify the mask, detect its corner for converting into a bird's eye view. For that, OpenCV comes to the rescue. We use convex hull contours method of OpenCV, approx polydiffy method to detect the corners, and then fed those corners into the OpenCV perspective transform function to get some bird's eye view, clear bird's eye view of the original image. Now I am handing over to my fellow team member for explaining the rest of the pipeline.
Good morning. After we have extracted out the monitor in bird's eye view, the next step for us will be to detect the locations of the vitals. We tried several different transformer-based models like Craft, Deep Text DTER, but they were not fast enough on CPU. So we decided to use our own model for detection. We chose YOLO V5 Nano because of its extremely fast speed and ease of trainability. Also, it uses mosaic augmentation, which crops out different parts of images and combines them so that the vitals can be detected irrespective of the class cell. And we also annotated more than 1000 images from the unlabeled dataset, which were selected cautiously from various classes which were not originally present in the labeled dataset to make the model more robust. All the vitals, along with the HR graph and MAP, have been extracted using the YOLO V5 Nano model with an inference time of 0.05 to 0.1 second. Next, we can see in the metrics that we have achieved exemplary results. All the three losses, including the box loss, the class loss, and the object loss, have converged to 0. and the precision recall and mean average precision have all converged to one, both in training and validation data set. Next, we need to find a text written in the bounding boxes returned by the detector model. We employed Paddle OCR for that, which is an open source detector and recognition model, but we only use the recognition part of that model. We also did post processing on the predicted results based on the layouts of the monitors, which will be further discussed in the novelty section. Next, we can see the framework of the OCR. Here we can see overall layout of the Paddle OCR model using the bounding boxes from the YOLO V5, the detector model that we used. We have only used the recognition feature of the Paddle OCR. Its recognition feature is fast and uses augmentation so that the model can detect stretched out, blurred, or rotated text. Next, the added attraction to our pipeline is digitizing the HR graph. We used WebPlot Digitizer, an open source Python library, and modified our graphs for that digitization. What kind of modifications did we do? In our graphs that we extracted out, there was text written on the graph. We found out the contours of the graph, then use erosion and dilation to remove those texts, and then pass through the digitizer to get the digitized version of our graph. And that was quite accurate. Now, concluding on the pipeline, I would like to throw some lights on numerous novelties that we incorporated on various aspects of the model, starting with speed. Instead of doing processing sequentially, we are doing it parallelly on multiple threads of CPU, which increased the speed to more than 2.5 times. We use the smallest version of YOLO V5, which is the YOLO V5 Nano for detection, which is fast and also did augmentations like mosaic augmentation. Also, we carefully chose the size to pass through the YOLO V5 detector model, and the size were chosen as can be seen in this histogram. The sizes, we plotted the histograms and found out the most commonly occurring sizes in both height and width so that there is least information loss. Next, in terms of accuracy, our novelties include that we applied some post-processing rules. The rules include rules like the SBP and DBP were always close to each other, separated by a slash between them. The HR graph and HR were also close to each other. We used confidence returned by the detector model because of that confidence we could sort out what was the best detection, and map was always inside the bracket, so we found out that too. We used segmentation for pixel wise accuracy, and we did data augmentation which was unsupervised, which was discussed earlier. But this was all about the problem statement. But wouldn't it be better if there was a better user interface for using that model? For that, we went one step ahead. We have used the Gradio visualization tool, which can run the model directly on a local host. A user can run the model directly on a local host by uploading an image and finding out all the vitals along with the HR graph and its digitized version. And that was all about our model. Thank you.
Um, Good one. Good job on like that segmentation model. Like you guys like did recognize that like all monitors are not of like rectangular shape. Good one on that. Pradeep, like you can ask.
Okay, for digit classification, right? So can you go to that slide?
1 second.
Yeah. No, digit classification.
In this part, OCR1.
Okay, when you digit detect when you run YOLO model, so how you are like classifying those digits? So say suppose like there is a high chance, right? So I think like you are just using YOLO model, right? Or are you doing like anything specific for like those digit classification?
So, sir, the YOLO model that we have used that has been trained to detect various vitals along with their classes, and it returns the confidences too of the various classes. Now, along with these
That as
confidences,
well,
as I
we have
explained
done.
later, we have also applied some rules to the model. These rules, like I said, that the HR and the HR graphs, they will always be close to each other. The SBP and DBP will always be separated by a slash. The map has brackets. And also some rules like SBP will always be greater than DBP for the yeah, always. And these kind of rules we have employed for detection.
Okay. So like third rule, I can like agree, but not with the first two. Do you like have any analytical data on that one? Like those two rules are like okay to like apply.
the, the first rule, that is SBP and DBP are always close to each other.
No, the first rule you said like HR will always close to the wave, right? And the second you said like it SBP and DBP will separated by slash.
Yes.
So like, yeah, I can elaborate on it on more. Like, we are not mentioning like they are always close to each other. Like out of all the graphs and the HR values that we got, the closest one will be like we are like suppose YOLO is detecting multiple graphs from the monitor, but we are assigning the graph like for HR it will be detecting multiple predictions, but we are assigning HR graph the one which is closest to the HR value, like so that it will we are rejecting those graphs which are not as close to the HR. Like we have not seen any layouts like that in the like more layout which have don't satisfying these rules. That's why.
Okay, some I think like some layout if you have checked it, right? So some layout have like more than one HR graph, so might be like two or
Yeah,
three.
yeah.
So in that
Yes,
case, like there is a digit beside like those graphs, right? So how doesn't it like confuse with HR with like SPO2 or anything?
yes, sir. Like those things we encountered, like there were some graphs, like there were multiple HR graphs as well. We have identified that, and model is giving both of them as HR, one with lower confidence and other with HR. But like we thought that we have to give only one HR graph as a problem like,
Uh,
statement. Yeah.
so my question is how you classify the digit, not the graph.
Okay. Yeah. Vedant, you can elaborate more on this.
Sir, so in classifying the digits, one more thing that we applied, that HR that number for the most part is close. See, three things come to picture when we apply the YOLO model. The one thing is that it always gives, if it in case gives HR and SPO2 both, which was the case in sometimes it detected HR and SPO2 both, but every time HR always had higher confidence uh, in the same detection. Also, we saw that HR was always like for the most part green in color, but uh, like if they are detected both, then we did some thresholding for green color, but that was not the case for all the monitors. So we used confidence and also its closeness to the HR graph. And SPO2, I don't think that was very close to HR graph, as close as HR. So, and HR was mostly confused with SPO2 only. Like it was never confused with SBP, DBP, or MAP. So that was the thing.
There can be like other numbers which are also very close to the HR number, right? So like 70, there is also other numbers as well.
Sir, but we have like the classes which we have put into training for HR model. Out of all of them, like most of the times HR was the closest one to them. Like the examples which we saw, like maybe we have ignored some examples out of the because there were 7,000 unlabeled data sets. So instead of like designing rules for each of them, like we focused on the algorithm which runs on most like on majority of them.
Okay, cool. So we can close this. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Sir, we can give a live demonstration if we want for the visualization, or is it good?
Yeah, it's good. But
Um,
we already have that notebook
Okay,
in.
okay, okay, sir.
Thank you.
Okay.
Thank you very
Thank
much.
you.
Thank you, sir.
Thank
Thank
you.
you, sir.
so Akash, like how many teams are like left?
We have two more teams left.
Okay.
Hey Rahul, are more members joining from your team? Or is it just you?
I think there will be more members. Just
Okay, okay.
please give me a minute.
Yeah, sure.
So one member will be with me and two other members will be joining. One member sitting right next to me. Both be using the same laptop.
So yeah, can you please turn on your video and request the others to join in ASAP?
Sure.
Hi, so there is an announcement for the team. So we'll be buzzing you in after 8 minutes and after 9 minutes and 30 seconds into your presentation. As a reminder, here is how the buzzer will sound. You can continue.
So shall we start?
Yeah, sure. We can start. A very good afternoon, judges. These slides will go over our solution to the vital extraction challenge. So the entire workflow is quite simple. We first worked on identifying the type of the monitor. We were presented with 4 classes. After we identified the type of the monitor, we performed segmentation to get the 4 coordinates around the monitor. We then used the cropped image of the monitor to identify which waves and which numbers corresponded to which vitals, respiratory rate, heart rate, SpO2, etc. We then obtained the cropped image of these vitals and then processed them to finish the challenge. So a good portion of our solution also revolves around YOLO, which is short for you only look once. So there's several popular object detection models like the faster RCNN, but while models like that create individual region proposals and infer on the individual regions, YOLO v5 works by dividing the entire image into a grid and passing the whole thing through a convolutional net in one shot. Therefore, it's often much faster than the faster RCNN. And that's why we used it for this problem. So for custom training, there are typically 3 approaches. So one approach just involves using a smaller model with fewer layers. You can also use a medium model with more layers, or you can also freeze a few layers of the medium model before training and then train it. But we found that for the current problem, it was sufficient to just use the smaller model as the inference time was reduced significantly. And the accuracy was also for this problem not impeded much. So we ended up using YOLO v5s. So as discussed previously, we used the V5S version of YOLO V5. It was configured to the image size of 640 pixels. 30 epochs were used, and the model was trained on a Tesla T4 GPU. So we use the YOLO V5 in this workflow in 2 places. One for the monitor detection and making bounding boxes around the vitals also it was used. So for the monitor detection, we used an 80-20 training validation split. And for the vital detection, it was a 70-30 training and validation split. The first step was cropping the monitor and getting the bounding box coordinates for the monitor. After this, some basic denoising and thresholding and image processing techniques were used. After that, the vitals were obtained and binarized for OCR. After this, the predicted values were finally reported as a dictionary. Now, Harshit will take you through the OCR part.
Thank you, Rahul. Okay, so OCR or optical character recognition is a technology that allows computers to recognize and extract text from images in scanned documents. It works by transforming 2D images into machine readable text. and it analyzes the pixels of images and uses various algorithms like deep neural networks to identify patterns that can potentially correspond to numbers or letters. So the working of OCR is as follows. So the first step is pre-processing, and it includes various steps like denoising, thresholding, binarizing, rotation of the image, removing the skew, etc. Then character recognition, and then segmentation based on the recognized character, and then post-processing, which mostly includes error detection and error correction, and then finally extracting the features based on what we have done. Next. So OCR is applied in many places. Its most common use is for digitizing documents like invoices, receipts, or even your passport, Aadhaar card, etc. It's also used by law enforcement for reading license plates. So some of the most popular open source tools for implementing OCR are given here, like they include Ocular, Octopus, and Swift OCR. We have used Tesseract for our application. So Tesseract OCR, it is an open source text recognition engine, and it's compatible with many programming languages. It can be used as a default without any existing layout analysis or in conjunction with an external text detector. So this is what the Tesseract OCR is based on. It's based on LSTM, which stands for long short-term memory. And the thing with LSTMs are they are great at learning sequences, but slow down a lot when the number of states is too large. So empirical results suggest that it is better to ask an LSTM to learn a long sequence rather than a short sequence of many classes. So Tesseract was originally developed from the Octopus model in Python, which in itself, it was a fork of an LSTM in C called CLSTM. CLSTM is an implementation of the LSTM recurrent neural network model in C++, and it uses the eigen library for various numerical computations. So PyTesseract is the implementation of the Tesseract OCR engine in the Python language, and it allows users to easily integrate OCR into many of their own personal applications. So the Tesseract is mainly used for these three different use cases: word detection, line detection, and character classification. Thank you.
The problem statement also asked us to process the HR wave. So what we did is after we generated the bounding box around the HR wave, we obtained the cropped image. We then scaled it and used some non-local denoising, and then we finally binderized it. We then spotted all the high pixel values and then reconstructed the wave. Then we found the baseline and the ECG signal and computed measures of central tendency like the mode. And then finally, we found all the PR peaks. Finally, the digital signal, the threshold image, and the original image were all plotted. Now, Rishit will take you through all the results we obtained.
Hello. We'll just be going into the solution part of what we have done and what we have obtained after doing this. So we'll start with the monitor part. So how we were able to identify the monitors. As you can see, the monitors were predicted mostly with near certainty from the given images from different types of the monitor. So as you can see, we have one type of monitor on the top left and another type of monitor on the bottom left. So it is able to detect all types of monitors and classify and drop proper bounding boxes that are compact ASAP. The next slide will show basically how our training model in YOLO V5 was able to classify the different parts of the monitor and put them accurately. You can see that the vitals like your heart rate, your mean arterial pressure, SpO2, everything are captured very properly in this training model. So this is a small video of how that works and how we are able to parse all the different parts of the monitor and we are able to display them together. So as you can see, the monitor has been predicted with a very good accuracy, and so are the other parts of the monitor as well, and we are able to display them as well. So apart from that, what we have is what we also have are the statistics. We'll show the confusion matrix that has arisen. We can see that most of the important vital information that every doctor needs has been given with near accuracy of 1. There are a few false positives on some side, and there are a few confusions with the graph and the background, but that is obvious because the graph is not very distinct from the background. And coming to the monitor detection waves, we can see that the training rate, the loss rate for the training and validated models is not is decreasing pretty fast, and the precision and recall are pretty close to 1 even after a few epochs. And when you come to the classification data set, what we have is that the training and validation losses are very close to each other, which is a good sign of generalization. And the class loss and the precision, everything is again approaching pretty good values. Precision is a bit low because of us getting very blurred images and other challenges that we faced, but we have improved that using our own algorithms to make sure that we are able to remove the ones that have very low probabilities and only choose one particular class for the entire monitor. Next, coming to the ECG part, we have thresholded the ECG properly from the cropped image and then consequently digitized it as shown earlier into the peaks, P and R peaks. We've also kind of predicted the S waves from the R ratio. So the final challenges that we faced.
I think we'll leave that to the Q&A session.
Yes.
Yeah. Thank you. You guys used Tesseract, right? So did you guys see about how much time that it took?
Tesseract has 1 second inference time.
Don't you think that's a little too big?
I think the few important features were MAP was surrounded with brackets, and SBP, DBP is surrounded with slashes. So for those things, Tesseract was allowing us to find the characters so that we can recognize these special characters. So we took a risk on that. And then for some of the OCR models like Paddle and all, Tesseract is better on CPU most of the time.
Okay. Can you go to the vital classifications slide?
The graph, sir?
No, the classification slide. Wait, let me tell you. So just walk me through how you guys are extracting, classifying the vitals as HR and all of that.
So using the annotations, box annotations, we classified them as the model predicted them, but it had a bit of inaccuracy. That time we had to use the basic medical knowledge we had, that a few of the values like SpO2 and RR, they're quite similar, and most of the time they are below. SpO2 is above RR, but it's pretty common that RR should any day be within the range of 10 to 30 or 40. 40 is also very extreme. Those are very rare cases. And SpO2 below something like 75 or this, the person is really in danger. So those are also pretty much impossible values. So anytime SpO2 should always be greater than RR.
So these impossible values, right? So these cardiac monitors are in critical in ICUs. So most of all of the patients would have critical values, and almost there's a lot of chances every day that we see almost impossible values.
So sir, these are biconditionals. One thing was SpO2 was always above RR. So we were just connecting with the bounding boxes from annotations, and after that we were also checking these values. So SpO2 should anytime be greater than RR.
So some other specific things were done. So for object detection, these models are trained to just, if they cross a certain probability threshold, they'll output 2 boxes for the same thing, right? So we also use certain techniques where if there were 2 predictions for respiratory rate, for instance, we just took the higher probability one, and that dramatically improved our precision. If you looked at the recall, you'd see that the recall is at 1, which means it's getting all the values, but the precision you'd see was at 0.8. Because models like the YOLO V5 often predict the same class more than once. So there were some false positives. So whenever we could, we opted for non-ML techniques to dramatically improve scores like precision. We just took the highest probability, and this immediately eliminated a lot of the false positives.
Okay.
Okay, about those metrics you are saying, like you got a recall rate of 1. So in which test data set you have like checked that one?
Classification data set and
Yeah, classification data set we have provided, right?
yes, sir.
The multi-class classification.
Like
Yeah.
all of them were at once. We didn't use them separately.
Okay, but
we made a.
What I'm asking is there should be like a data distribution. Like there should be a data distribution for training. There should be a data distribution for validation, and there is another data distribution called the test set. So test set should be like unseen to the model. If you are training on the test set, there is no point of like testing it. You will get a recall rate always 1.
I think the recall was based on the validation. It wasn't. It was unseen data.
Unseen data, yeah.
It was not on train.
No, validation data is different. So see, we have like these words, right? Test and validation. There have some meaning behind these words. So validation, you can like tweak your model to like set to like one particular validation point and stop learning it. Test data is like completely different. It should be like unseen data.
We use the unlabeled data set provided as the test set.
Okay, then what is the validation set, and which model you have like used?
YOLO V5.
Yeah, YOLO V5 has like lot of models.
V5S.
S model. Okay, so what was the data size that you have trained on?
1,000 and 1,000 for the first, 2,000 for the monitor, and 1,000 for the like the second part, classifying the vital signs.
Okay, do you think like 2,000 images for enough for like S type of like model? Do you know like how many parameters it has?
Yeah, like hyperparameters were the image size and the.
No, we are not talking about hyperparameters. We are talking about trainable parameters. It's a different thing.
We found it was sufficient. Like based on all the curves, we found that the prediction scores were quite high. So
yeah, but like see, you saying recall rate is 1, right? So there is a like higher chance like your model is overfitting to the particular
the
validation
training
set.
and the validation curves were very close in terms of value. So it could not have possibly been overfitting.
I'm not sure. Like, see, like if we have like or tested on test data set, we will get the result.
Even on the test data set, I think we got similar results. Basically, in the beginning, we got overfitting when we were training the smaller set, and we found widely differing losses between the training and the validation. That signaled overfitting. So we just basically lowered the model complexity, and this ensured that overfitting was no longer a problem. That's why the differences in the validation and training losses wasn't much in the graph you saw.
That can be achieved with like just reducing learning rate.
Sorry?
That can be just achieved like the parameter you are saying in the graph fluctuation, right? That can be achieved with reducing learning rate. So I'm asking about like you are saying it's a very highly accurate, right? Recall rate is 1. So I'm saying it's impossible.
It's a very, very simple classification. If it just spots, we took the crop monitor.
It's not a simple classification. If you have not seen the data.
The spatial locality is roughly the same for a given monitor type, right? So the recall will most usually be very high, because the model's parameters pick up on.
So what's the recall? What's the recall you mean by recall?
Recall is just how often whatever is there we get.
No, the definition of recall.
Recall is just like predicted positive by actual positive.
Okay, that might not be there, but okay. Okay, thank you guys. Thank you.
Thank you. We'll close this. Thanks.
Thank you, sir.
Hi team, can you please switch on your mic and cameras? Sure. Also, there's an announcement. So we'll be buzzing you in after 8 minutes and after 9 minutes, 30 seconds of your presentation as a reminder. Here is how the buzzer will sound. We'll start now.
Yeah, guys, like please start.
Yeah. Yeah. Hello, everyone. We are from Team 41, and today we'll present our submission for the submission challenge. So the problem we have at hand is twofold. We need to extract the values and digitize the graphs of various vitals present in the ICU monitor screens. To solve this problem, we propose the following pipeline. At first, we do image segmentation. That is, we take images of the ICU rooms and identify the monitors out of it. And then we detect vitals on those monitor screens. That is, we form bounding boxes on the values of the vitals and bounding boxes on the graphs of the vitals. So we pass the values to an OCR model to get the values, and we pass the bounding boxes on the graphs through a graph digitization module that we wrote ourselves. So let's take a deeper look into the monitor screen extraction step. That is the first step of the pipeline. So this is what we start off with. Um, so we do an unsupervised SimCLR contrastive learning training on the unlabeled dataset, and then we fine tune on the labeled segmentation data. So we use ResNet 50 and ResNet 18 for this. We observe good performance on the training data, but unfortunately, we observe unsatisfactory performance on the unlabeled data. Intuitively, this might be because we are solving a regression problem using the MSE loss for the ResNet. And this might not generalize well to the case of unlabeled dataset. We tackle this issue by converting this regression problem into a classification problem using cross-entropy loss, and we use segmentation models for this. So this slide provides the theoretical justification for this, but in the interest of time, we'll take questions on this later. So here's how we convert this into a classification problem. So using segmentation models, as an input, we have the entire image of the ICU rooms, and in the output, we have 4-channel heat maps, one for each corner. So the output of the segmentation model gives us this probabilistic prediction for each corner, and this is the ground truth corner. We compute a cross entropy loss between these two to get our prediction. So one obvious way to do this is to use the UNet model, and it achieves really good results on this. But this UNet has a very high inference time. So we shift to the segfarmer model, which is much more recent, has higher accuracy and faster inference. So here's a performance comparison for the segmentation models. Down here, you can see the performance of UNet and segfarmer. It's really good. And ResNet does not clearly generalize to the unlabeled dataset. And segfarmer has a much faster inference time of 0.7 seconds and a better validation score as well. And both of them are like good on like 6,950 images out of 7,000 images.
Okay, so let's move on to the next part of monitor classification and vital detection. So initially, our approach consisted of classifying the input monitor screen into 4 types of layouts. and then applying an object detection module like YOLO on it. But then we realized that this makes our pipeline unnecessarily large and having to load 4 different YOLO models on it. And we also realized that YOLO was capable of handling different layouts present in the dataset without the requirement of an explicit classification model. So we bypassed the classification process and directly used YOLO V8 for the vital detection task. So, however, we observed a poor performance on the unlabeled dataset. Our intuition behind this is that our approach was not able to handle different types of layouts, different and the out of distribution nature of the unlabeled datasets from the labeled classification data. So we decided to propose a new dataset generation technique. So in this, we take the unlabeled dataset and pass it through a feature extractor to get the features of each image, and then we use clustering. And then after we have the clusters, from each cluster we sample around 30 to 35 images and merge them to make a custom dataset, and then we manually label them. And finally, we apply some random data augmentations to generate the final custom data. Yeah. And in this slide, you can clearly see that the YOLO model, which is trained on the new custom dataset, clearly performs better. And by our intelligent labeling of the unlabeled data, we can see that it certainly helps here. So to further improve the performance of our YOLO model, we use a text detection module called as Craft. So I'll give you a general overview of what Craft does. So it basically takes an input monitor screen and outputs a probabilistic heat map, where the heat map represents the regions in the input screen where the probability of text being present is very high. So how do we improve the YOLO V8 performance using Craft? So we take the output of the Craft, that is the probabilistic heat map, and multiply it with the input original input image, so that the resultant image will have distilled information, as you can see in these left images. And and from the map 50 values shown on the slide, you can certainly see an incremental improvement in the YOLO V8 performance. But since this improvement was incremental, and addition of the Craft module added 0.7 seconds of overhead in the inference time, we decided to skip this enhancement step. So the next part is the optical character recognition, or the OCR part. So we used 4 different types of OCR models, and we found out that the Parsec Tiny model works best in terms of runtime, and also it does not require any kind of pre-processing. In this slide, you can see the results of the Parsec Tiny on some of the worst images we observed in the dataset, like the 60 and the 56 image are some of the worst images we observed, and the Parsec Tiny model performs very well on this.
So for the graph digitization, we wrote our own module for this. So we get the waveform image from the YOLO V8 bounding boxes, and we do a series of pre-processing steps on it. First, we pass it to a median filter to get rid of the noise. Then we select the green channel for the heart rate wave. Then we binarize the image, do a canny edge detection on it, and do contour detection. So this contour graph is what we need for our algorithm to work. So there's an algorithm we propose in the next slide. Our algorithm takes in this contour graph and outputs this digitized graph. So as you can see, the contour graph might have some artifacts or occlusions like this text over here, but our digitized graph does not have that. Our algorithm gets rid of it. So also our digitized graph is in the form of numbers, like a series of numbers. For every X value, we have a single Y value. That is, we take this contour graph and convert it into a digital function. So the novelty in our submission is threefold. First of all, we propose the quadrilateral bounding box problem in the image segmentation task as a 4-channel classification problem. So this is not how usually segmentation tasks are done. So this is certainly something novel, and it works really well. And secondly, we utilize Craft to highlight regions of interest to further distill information for YOLO V8. This is, even though this gives incremental gain in performance, this is something novel. Thirdly, we design a novel algorithm for graph digitization under the presence of artifacts. Yeah, and the average inference time of our pipeline is 1.8 seconds. This is tested over 200 images, full images on Colab CPU. So this is just an illustration of our pipeline in action. First, you can see the original image. We have the image of the ICU room. Second, we get the segmented image using our segfarmer segmentation model. Then we get the vitals detected using our YOLO V8 object detection model. And finally, we have the extracted vitals and waveforms. So the vitals detected are using our OCR parsec tiny model, and the waveforms are using our own graph digitization model that we wrote. Thank you.
Thank you. I've liked like that heat maps and like using the craft and like the especially good job on the digitization as well. That's like really well done. So one comment was that like you didn't like use that heat maps like feature because like it was increasing your inference time, right?
Yeah.
So sometimes like it inference rather than inference times, like some sectors like would actually rely more on accuracy. So like for example, like vital accuracy is like much more important in the healthcare like sector, because like so here when we are going to take vitals, so the vitals are collected to understand the trend if a patient health is deteriorating or not. So like so you can take an image, so sometimes it's over like every hour you take, sometimes it's like 2 hours. So based on like different industries, like you would want either accuracy or like inference as well. So that was my comment. Pradeep?
So I want to ask, like, so you are extracting region of interest, right? So are you
Yeah.
using those parameter in any way, like classifying those digits?
In this part, the craft part, you mean?
Yes, in craft part.
I think I'll ask Ruchit to take the question for this.
Yeah, so we are not really using any parameters to classify. So we are using this craft and then merging it with YOLO. And YOLO is doing the entire classification problem.
Hey, can you like repeat it? Because like two of you were on the same room, right? So
Okay.
yeah.
It was echoing.
Yeah. So basically, we are not using craft directly. We are merging it with YOLO V8. And YOLO V8 handles the classifying the bounding box with respect to which label it is exactly. So craft is just increasing the chance that there is a bounding box and we detect it correctly.
Okay. So, okay, there might be a like way to like use this one, right? So if you have not like, I think use the transformer architecture. So it's work on like similar principle. So it's a feedback loop when you like pass this one. Like the weightage of the you enhance the weight, right? With for the like specific region.
Yeah. This is sort of providing attention on the important parts of the image.
Yes, that's the attention.
That is true. Yeah.
And this one as well, like you guys use a custom data set as well, right? Using clustering and all. That's also a good approach. So good job on that. I don't have any questions. Pradeep, do you have?
No.
Okay, so we can close this. Thank you, guys.
Thank you. Thanks a lot.
Thank you.
Thanks a lot.
Thanks.
So